Hello dear listeners, dear students, we'll continue lessons partial derivatives, Higher Mathematics 2 course, lecture 3. If the point x0, y0 is a point in the domain of a function f of xy, the vertical plane y equals to y0 will cut the surface z equals to f of xy. In the curve z equals to f of x, y0. This curve is the graph of the function z equals to f of x, y0 in the plane y equals to y0. The horizontal coordinate in this plane is x. The vertical coordinate is z. The y value is held constant at y0, so y is not a variable. We define the partial derivative of f with respect to x at the point x0, y0 as the ordinary derivative of f of x, y0 with respect to x at the point x equals to x0. To distinguish partial derivatives from ordinary derivatives, we use the symbol d, this kind of d, delta or maybe, rather than the d previously used. In the definition, h represents a real number, positive or negative. This figure shows the intersection of the plane y equals to y0 with the surface z equals to f of xy. This is the surface, this z equals to f of xy, it's shown here. Y equals to y0 is the plane, which is this one, y equals to y0, because this point is y0, this is the plane. So this plane cuts the surface z equals to f of xy. And when it cuts, it will have this kind of blue line. In the cutted place, we will get this kind of blue line. And we're taking the point P, which is x0, y0, and f of x, y0, x0, this point. And we want to calculate the derivative at this point. We would from above the first quadrant of the xy plane. So we want to calculate the derivative at this point. The partial derivative of f of xy with respect to x at the point x0, y0 is this expression. So we always write df dx x0, y0 equals to limit when h tends to 0 f of x0, sorry, it must be this kind of f of x0 plus h y0 minus f of x0, y0. If you look carefully here, we are holding y0 as a constant. y0 constant. So we may calculate the derivative at point when x equals to x0. Provided limit exists. If this limit exists, derivative we can calculate. We may write in different ways. df dx x0 y0. This is the first way, or f small x here x0 y0. The small x in the index, it means partial derivative of f with respect to x, or dz dx with this kind of line x0 y0, the point which we are calculating derivative, or just f x in the index without the point, or df dx dz dx, sorry, x, or z, the small x. All of them means the partial derivative. Partial derivative of z with respect to x. Partial derivative of f with respect to x. Partial derivative of f with respect to x. The partial derivative of f of xy with respect to y, at the point x0, y0, is this expression. Again, the similar expression here we may see here df dy and x0, y0 here, which is equals to d over dy f of x0, y. And this is at y equals to y0, which is limit h tends to 0 f of x0, y0 plus h minus f of x0, y0 over h. If we look carefully here, we are taking x0 as a constant in this case. x0 is constant, so we can calculate the derivative with respect to y. The slope of the curve z equals to f of x0, y0. At the point P, x0, y0, f of x0, y0. In the vertical plane, x equals to x0 is a partial derivative of f with respect to y at this point. The tangent line to the curve P is the line in the plane x equals to x0 that passes through P with this slope. The partial derivative gives the rate of change of f with respect to y at this point, x0, y0, when x is held fixed at the value x0. For the partial derivative of a function with respect to y, also we may use df dy x0, y0, or f small y here, x0, y0, or just df y, or df dy, or maybe dz dy z y, this kind of. We may use any of them, all of them correct. And here that graph, which we have mentioned in the previous page, the intersection of the plane x equals to x0 with respect to surface z equals to f of xy. Viewed from above the first quadrant of the xy plane. So this is our surface, z equals to xy, this one is surface, this is the plane, x equals to x0, and it's cutting here, and we got this blue line in the cut place, this blue line, and we are calculating derivative at point P, at this point, and the red line is tangent line. So I think it's understandable because it's similar with the partial derivative of a function with respect to x, and this is the partial derivative of a function with respect to y. So in this example it says to me find the values of df dx, which is partial derivative of f with respect to x and partial derivative of f with respect to y at the point 4, -5, if the function is in this form. So first of all, I have to calculate the partial derivative and then plug in the point. So df dx equals to, what is f? F is this function, just wrote that one, dx, the function is x squared plus 3xy plus y -1 equals to, so take derivative from x squared with respect to x, gives me 2x plus 3xy, 3 is a constant coefficient, multiplied xy, multiplied xy, derivative of xy gives me y, because we are calculating derivative with respect to x and y is held constant, y, plus derivative of y becomes 0, negative derivative of 1 becomes 0. So 2x plus 3y. Just place these points 4 instead of x, 2 times 4 plus 3 times -5 equals to 8 minus 15, -7. So this is df dx. And now let me calculate the df dy also. You may also see the df dy in the next page. So df dy equals to dy, this is d x squared plus 3xy plus y minus 1. Close the parentheses. Derivative of x squared with respect to y is 0 plus derivative of 3xy, 3 times x, plus derivative of y gives me 1, -1 is 0. So 3x plus 1. Plug in numbers, 3 times 4 plus 1, 12 plus 1 gives me 13. This is the derivative of a function with respect to y and at the point 4, -5. So good luck guys, this is the end of W.R.TY. See you in practice.